Okay, so we're going to start in Chapter 1. And Chapter 1 has a whole bunch of definitions in it that will help you understand what the book is talking about later on in various problems. Just like with any new subject, there are words that are particular with statistics, and you need to learn those words in order to understand what's going on. So the very first slide here is what is statistics. This is the class statistics. Statistics is learning about a large group by examining data from some of its members. Polls, studies, surveys, and other data collecting tools collect data from a small part of a larger group so that we can learn something about the larger group. So what is statistics? What are you studying in this class? In statistics, we're learning about a large group by examining data from some of its members. We do this all the time in the real world. Last year's election, you saw poll after poll saying who was winning. Various studies and surveys and every other things. We see them on television all the time. We hear them on the radio. They're all over the internet. It's how business people or politicians or just anybody, research teams, try to figure out how people think about something or whether something works. And generally to do that, we take data from a small part of a larger group to learn something about it because it's usually hard to do the entire group. And we'll talk more about that as we go. And this is what I said at the beginning. You're going to be presented with many definitions this chapter. Memorize them so that you can apply them. There will be quizzes. It will be on your first test. And it's to help you later on, because knowing the terminology helps you in future problems. As I said, there's a lot of definitions in this chapter. You want to memorize these definitions to be able to apply them. So let me explain what I mean by that. Like on the notes that you're looking at, the first definition is for data, which is collections of observations. That's not what I want you to memorize. I don't want you to memorize it where you can write it out or match it or anything like that. I want you to be able to apply it. If you look down farther on the page, there's some examples, and I'm asking you what the population is, what the sample is. And there's a definition for population and sample above that. You have to know the definition in order to be able to answer those questions. So that's what you want to do in this chapter. You want to memorize these definitions in order that you can apply them to problems. So your very first definition is data. Statistics is all about data, collections of observations. And data can be absolutely anything that you have a question about. It could be measurements, it could be genders, it could be survey responses. So absolutely anything that you have a question about is considered data. That didn't sound quite right. What you have a question about, you make a question, then you collect data in order to answer your question. So that very first definition, data. Data is a collection of observations, and usually we use the variable x to represent data. This can be absolutely anything that you're interested in studying, anything you have a question on. It could be measurements, say heights if you're interested in something about how tall people are. It can be genders. It could be survey responses. So data is what you collect in order to answer a question you have. Okay, now, statistics, the subject that we're studying, is the science of planning studies and experiments, obtaining data, and then organizing, summarizing, presenting, analyzing, interpreting, and drawing conclusions based on the data. You'll be doing all these things in this class. Now here's the first definition you really need to memorize. Population is the complete collection of all individuals to be studied. You want to underline that word all. That's how you know it's a population, because it's all of them. So all adults in the United States, all IQ scores for high school students in Tennessee. Population is all, every last one of them. When we actually get our data from a population, it's called doing a census. In the United States, we do a census every 10 years. In that 10 years, they try to get absolutely everybody in the United States, well, every adult in the United States, to answer a survey about certain questions. And this is very important. A lot of political boundaries are drawn from the census. Businesses decide whether to locate somewhere based on census data. A lot of socioeconomic things are decided from census data. A lot of money depends on the census data. So it's important for the census to be as correct as humanly possible. So you try to get absolutely everybody to answer the census. Because if you have an entire population, you know your numbers are exactly right. A funny story, back at the last census, where I live, I have a mobile home, and then up the hill is the house that we built. We lived in the mobile home for a long time, and then we built a house up the hill, and we live up there now. The mobile home has trees literally growing out of the front door now, and I had 3 census workers come up to the house and ask me if anybody lived in the trailer because it still has its own address. So they are very determined not to miss anyone when they're doing the census. We only do a census every 10 years because it's extremely impractical. It's hard to get everybody to answer something. It takes a lot of time and money and effort. They paid 3 people to walk up to the house to see if anybody lived in that trailer. So normally, we don't do a census. Normally, we do a sample. A sample is a subcollection of members selected from a population. So almost all the studies, polls, etc. that you see in the media are samples. They picked a group of people, asked them questions, and then made generalizations based off of that. So they might have asked 100 adults a question, and then they say all adults in the United States think this based off this sample. A parameter is the numerical measurement we get from the population. So when you did the census, if it said that 75% of adults in Tennessee are Caucasian, that would be a parameter because it came from a census. So parameter comes from population. Statistic comes from a sample. Usually the numbers you hear thrown around in the media are statistics. So if it said 75% of people in Washington County are Caucasian, then that is probably a statistic from a sample unless you know it came from census data. Okay, so here's the first example of how I want you to know these. I want you to be able to answer questions like this. So you've got all those definitions we just talked about. Like I said, I don't want you to memorize them verbatim. I want you to be able to use them. So, suppose on the test I gave you this question. Suppose a farmer wants to learn about the weight of his bean crop. He randomly sampled 200 plants and measured the weight of the green beans on the plant. What is the population? So, what is all in this case? Well, what's the farmer doing? He is measuring the weight of green beans on the plant. So he's wanting to know something about the weight of his green beans. So the population is all green beans. Now, it's not practical for the farmer to pick every last green bean, to weigh them, to know how much the average weight is. So instead, he did a sample, and it tells you there he randomly sampled 200 plants. So the sample is the 200. Well, let me say that again, because that's not 100% right. Because we are talking about the green beans, not the plants. So, the sample is the green beans Let me try this stylus and see if it does any better than my finger. From, well, no, actually, isn't that sad? Yeah, that's worse. All right. Let's try again. From the 200 plants. I'm new at this program, so I'll get better at this writing stuff as we go along. So, the population in this case is all of his green beans, because that's what he's interested in. He wants to know something about the weight of green beans. I could get more specific and say all the green beans in the farmer's green bean crop. Because all green beans, if you really want to be picky about it, are all the green beans anywhere ever in the world. So, if I want to be careful, I would say all the green beans in this farmer's bean crop. Then the sample is the green beans from the 200 plants he selected. Okay, so now hit pause on your recording and write down what you think the answer to this is, and then hit go and see what I tell you the answer is. Okay, so we've got, suppose a doctor wants to determine the average heights of his 3-year-old patients. He selects 52 of his patients and records their heights. What is the population? Well, again, let's look for the question. He wants to determine the average. Okay, so the population would be the average heights of his 3-year-old patients. So again, like the green bean example, we're interested in the heights of his 3-year-old patients. So that makes the population all the 3-year-old patients of this doctor. Now the sample would be the 52 that he selected. So the sample would be the 52 3-year-old patients that he selected. So population is all, sample is the part that we took to record the data from to make an assumption about all. Okay, again, push pause and try number 3, and then push play when you're ready to hear the answer. Hang on. Okay, in a recent survey, 2,490 adults in the United States were asked if they check their email accounts at least once a day. 48% of the adults said yes. What is the population? So we're trying to find out whether adults in the United States check their email accounts at least once a day. So the population, the people we're going to ask this question to, is adults in the United States. So again, population is all, so that would be all the adults in the United States. What is the sample? Well, we didn't ask all the adults. We asked 2,490. So the sample is that 2,490 adults that we asked. Then the final question asks, is the 48% a parameter or a statistic? Now remember, parameter comes from population and statistic comes from sample. So because this is a sample, our 48% would be a statistic. 48% of the 2,490 adults in the United States said that they check their email accounts at least once a day. It's only a parameter if this had come from a census, and a census would have been all the adults in the United States. Okay, so let's move on to our next set of definitions. Well, I have all of these in class, so this is just to kind of get you started on them. Okay, the next set of definitions further breaks down data into quantitative data and categorical data. Quantitative data consists of numbers, numerical data representing counts or measurements. These are numbers that it makes sense to average, like weights, heights, age, most of the numbers we're used to thinking about. Categorical data consists of names or labels representing categories, like hair color, type of pet, grade in school, data that isn't a number. This is also sometimes called qualitative data. So sometimes in my stat lab, you'll see qualitative data instead of categorical data, or in other books you'll see qualitative data instead of categorical data. Numbers can also be categorical data, but they have to be numbers that doesn't make any sense to average. Say phone numbers. If I took all your phone numbers, added them together, divided by how many there were, does that tell me the middle person in class's phone number? No, it doesn't. Whereas if I took all your heights and added them up and divided by how many there were, that would tell me the average height of the person in the room. So if adding numbers up and averaging them makes sense, it makes it quantitative data. If it doesn't make sense, like phone numbers, jersey numbers, that the average is not like the middle person, that is categorical data. So now you have several on your sheet to decide whether you think it's quantitative or categorical. So again, hit pause and then come back after you've answered all those and see if you're right or wrong. I'll write the answers down on here. I'm just going to put a Q for quantitative or a C for categorical. So gender. Gender is considered categorical because it's a label. Temperature. Temperature that I'm thinking about is like 70 degrees Fahrenheit, something like that. So that would be quantitative. If you thought of temperature as just hot or cold, then it could be categorical. But in general, when you think of temperature, you're thinking of a number. And it's a number that makes sense to average. If I took all the high temperatures for the year and averaged them, I'd have an average high temperature. Eye color, again, is categorical. Eyes are brown, blue, green. Those are labels, so that makes it categorical. Okay, the next one is zip code. Now, zip code is one of those categorical numbers. It's a number, but if I add all your zip codes up and average it, it doesn't give me any indication of what average zip code you come from. In fact, it'd probably be a zip code that none of you have. So zip codes are categorical. Average salary of a faculty member at Northeast State, well, that's quantitative. It's numbers that I can add up and average, makes sense. Number of days during the past week a college student has worked. Again, that's quantitative. If it had just said days during the past week a college student has worked, that could have been categorical because that would have been like Monday, Tuesday, Wednesday. But since it said number of days, that made it quantitative. Okay, Social Security number, this is another one of those categorical numbers. Heights of males, it's quantitative. And number of times a 2 is observed after rolling a dice 15 times is quantitative. And again, you'll get more practice with those. And when you come to class tomorrow, the first thing I'm going to ask is, did you have any questions from this video? So if these or some other part of it doesn't quite make sense to you, ask me. Oops. Okay. The next set of definitions. The quantitative data can be further broken down to be discrete or continuous. So our data that is numbers that we can average, that makes sense to average, we can break down into discrete data and continuous data. Discrete data is counting numbers. So it's like 0, 1, 2, 3, where fractions or decimals do not make sense. My example down here is chicken eggs. Chickens don't lay half eggs. It makes absolutely no sense for a chicken to lay a half egg. If there is a half egg, it's broken, you're going to throw it out. So you only think of chicken eggs as 1, 2, 3, or 4 eggs. You never think of 3½ chicken eggs. So discrete data is where a fraction or decimal just doesn't make any sense at all. It only comes in wholes. Continuous data is all the data that fractions and decimals does make sense in. Example, cow's milk. When you milk a cow, you don't get 1 gallon or 2 gallons or 3 gallons. You might get 1.4 gallons. You might get 2 gallons, but it's not going to jump from 1 gallon to 2 gallons. Anywhere in between there is a completely possible number. So again, you've got a few examples there to decide whether it's discrete or continuous. Again, hit pause in the video, put what you think, and then come back and get the right answer. For discrete, I'm going to put a D. Maybe I am anyway. There we go. And for continuous, I'm going to put a C. So the amount of water in a cup in ounces would be continuous. I could have 1.2 ounces. That would make perfect sense. The number of desks in a middle school classroom is discrete. I have 1 desk, 2 desks, 3 desks. A broken desk does not count. It's no longer useful, so it's not a desk. Number of cars in a grocery store parking lot is discrete. Those little smart cars may only be half a car, but we still count them as a whole car. The weight of an elephant in pounds is continuous, because an elephant can weigh whatever, 1.3 ton, whatever. I don't know what elephants weigh. Okay? Again, if you have any questions on these, ask me tomorrow in class. Alright, now this set of measurements is still another way to classify data. These are the ones that tend to confuse people the most. Nominal and ordinal are both categories. Oops, well that didn't work at all. Let's try that again. Okay, so they're both categories. So first, for it to be nominal or ordinal, it has to be categorical. So it has to be one of those labels. Interval and ratio, either one of those can be quantitative. And I'll explain the differences in them here in a few minutes. But that's the first thing. So first you're going to think, is it categorical? If it's categorical, it can be nominal or ordinal. Is it quantitative? If it's quantitative, it can be interval or ratio. Okay, so starting with nominal. Nominal is categorical data with no order. So if there is not a implied accepted order to name these labels, it's categorical. So for example, colors. If I asked different people in the class what their favorite colors are, they might name the same colors, but they probably wouldn't name them in the same order. You probably would say your favorite color first, and then some other colors that come to mind. Ordinal, on the other hand, is categorical data with an implied order. So if the first example I said, if I asked you favorite colors, you'd tell me colors, but they wouldn't be in the same order. But if I asked you color of the rainbow, you'd all tell me red, orange, yellow, green, blue, indigo, violet, because we all learned Roy G. Biv for colors of the rainbow, so we would name it in that order. It has an implied order. So colors of the rainbow would be ordinal data, where favorite colors would be nominal data. Interval is quantitative data, but it doesn't have a natural zero. There's no natural zero, which means there's never a time when none of the quantity is present. The two things that will happen that you will have interval data is temperature and years. Years like 1996, not years like I'm 30 years old. Okay? So if you see years or temperature, you know it's interval data. Because think about it. Is there ever a time where there's no temperature? Even if it's 0 degrees Fahrenheit, that still indicates a temperature. And in fact, if you change temperature scales, 0 degrees Fahrenheit is 30 degrees Celsius. So it's still got a temperature. And same thing with years. There's no time when time didn't exist. So even if we named something 0, it doesn't mean time didn't exist then. So anything like years, as in 1996, or temperatures like 36 degrees Fahrenheit, is interval data. All other quantitative data is ratio. So years like 30 years old. Well, there's a time when you were 0 years old and you didn't exist then. So it has a real 0. So any other quantitative data besides years and temperature, you will consider ratio. Okay, here again is some examples. Hit pause, try them on your own, and then hit go again to see the answers. Again, I'll use initials, so nominal. It doesn't like to start writing when I do. Nominal will be an N, ordinal will be an O, interval will be an I, and ratio will be an R. Heights of basketball players. Okay, let's think about it first. Heights is a quantitative data measurement, so that makes it interval or ratio. It's not temperature or years, so it would be ratio. Morning temperature at Tri-Cities Airport last week. Well, I just said the interval is temperatures or years, so that would have to be interval. Zip codes. Zip codes are categorical data. There's not an implied order to zip codes. Now, when I say implied order, I don't mean numerical order or alphabetical order. It's more that everybody says it this way. So if you were naming zip codes, again, you'd probably start with your own zip code and then any other zip code you happen to know. So this is nominal data. Distances traveled by students over Labor Day weekend. Well, distances is quantitative data. And it's not temperatures or years, so it's ratio. The actual contents in ounces of chips in a bag of baked Lay's labeled 10 ounces. Well, we're talking about the ounces of chips, which is a quantitative measurement. So that's ratio. Ratings of above average, average, or below average for new movies. Well, that's a categorical data measurement, and it does have an implied order. Above average is good. Average is okay. Below average is bad. When you were saying those, you wouldn't say average, below average, above average. You'd always put them in a certain order. So that's ordinal. The years in which statistics students in Math 1530 were born. Years are interval data. Okay, and the last thing we're going to talk about for this chapter is the basics of collecting data. Now, we've talked a whole lot about data. We've given it a lot of different labels. But we do have to get this data somehow. Statistical methods are driven by the data that we collect. If sample data are not collected in an appropriate way, the data may be so completely useless that no amount of statistical torturing can salvage them. And you don't know how true that statement is. The method used to collect the sample data influences the quality of the statistical analysis. There's two basic ways we collect data. One is observational study, in which we just observe and see what happens. And the other is experiment, which is like 4th grade science class experiment, that you set up something. In one group you give a pill, the other group you give a placebo, and you measure what happens. So observational study, we're just observing something that's already happened or as it's happening, but we're not affecting it at all. Experiment, we're doing something to affect an outline. So, which one of these is observation, which one is an experiment? Again, take a minute to do that. What you should answer is that the first one is an experiment. Maybe if I hit the pen first next time, it'll help. And the second one is observation. The first one, they took 300 people. They gave 125 of them an aspirin and 175 a placebo and measured what happened. In the second one, they just watched elementary students coloring in a coloring book. By and large, observational studies are the more common way that we get data. Experiments are costly, so unless it really, really matters that our data not be biased in any way, we're going to do an observational study instead of an experiment. The last thing we talk about in here is types of samples. Now remember, samples are what we do from populations. We take a sample, we gather our data from it, and then we make an inference about the population. The type of sample we do helps us to get good data or bad data. There are a lot of different samples because there's a lot of different ways of collecting data, and it depends on what we're trying to find out as to which one's more appropriate. You can do a sample in an experiment or an observational study. More likely that we'll do it in an observational study, but either way we can do these types of samples in either one. Now this very first slide is not on your handout. It's not on your notes really. There are two types of samples that are called random samples. If it just says random sample, that means that members from a population are selected in such a way that each individual member in the population has an equal chance of being selected. Whereas if it's a simple random sample, which is often abbreviated to SRS, members from the population are selected in a way that each sample size of size n, or each sample of size n, has an equal chance of being selected. So in a random sample, every single member has a chance of being selected. In an SRS, each group of 10 has an equal chance of being selected, or 20, or 30, or 100, whatever. In this book, but I wanted to make the distinction first because other books may be more picky about it. So in this book, a simple random sample is just called a random sample. So you don't have to worry about the distinction for this book. But just to let you know, not all books are that blasé about it, so you need to know that there could be a difference. So that first definition there on your notes is random sample. And I always think about a computer when I think about this, because generally, if we're going to get a random sample, we're letting technology pick it for us. Human beings are by nature biased, and if we pick it, we usually do something to make ourselves pick one or the other. So generally, it's better to give the computer the information and tell it to randomly pick us 100 or so out of whatever we gave it. Random sampling is the best because it has the least amount of bias. And I've said bias several times, but I didn't really define it. Bias is anything that affects the study. So it's anything that causes the data to be more one thing or more of another. Anything that affects the study at all. There's all kinds of bias, and we'll talk about them as we go along. So random sample is actually the best for eliminating that bias, but it's not always the most practical one to do. Another type of sample is a systematic sample, in which we select some starting point and then select every kth element in the population. In this case, our kth element would be 3, because we do 1, 2, 3, and then we pick that person. And we do 1, 2, 3, and we pick that person. And then if we did it again, it'd be 1, 2, and then 3 would have been this person who's not here. So in this case, we would only have these 2 people in our sample. The K can be absolutely any number you want it to be. If you had a whole bunch of stuff to sample from, you'd probably pick a bigger number. If you had a small number to sample from, you'd pick a smaller number. I often think about this as auditing files. If you were auditing files from some company, you don't want to pick them all out of the top file drawer. Those are the good ones. That's the ones they fixed before you came. You want to get them from all the file drawers. So if they had 1,000 files, you might decide you're going to pick every 100th one. So you just go through to 100, pick it up, 100, pick it up. This is also like quality control in a factory. They might pick up every 25th bottle and then sample it to see if it has the correct number of ounces in it. So even though systematic sampling has bias, because once you pick this guy, these 2 had no chance of being selected. So that made it not random, but it's still a good sampling method if you need to make sure you're getting so many throughout the population. Convenience sampling is the worst kind of sampling. It's results that are just easy to get. Even though it's the worst kind of sampling, it's still appropriate in different scenarios. If any of you have gone to a theme park in any recent history, you'll have noticed on your way out of the theme park, there's somebody standing there with a clipboard who wants you to ask questions about how your day at the park was. That's a convenience sampling. But who else are they going to sample, really? They can't stand in Walmart's parking lot and ask how your day at Universal Studios was. But it is still more biased. And especially think about if you were the person standing there with the clipboard. Who are you going to ask to answer your questions? You're not going to ask somebody who looks very angry or who's got 5 kids in tow and are just dying to get out of the park. You're going to ask people that are smiling, who make eye contact with you, usually older people because they don't mind to take the time to do it. So the results that you get would be biased because you're a human being and you're going to pick people that you think will answer your questions. But it still has its point. So if I was the owner of Universal Studios and this clipboard survey indicated that people thought the price of drinks in the park were too high, then what I might do to get better data is do a random sample of my mailing list and ask that same question and see if I got a percentage that seemed high there. So convenience samples can be a way to get data to give you an indication of which direction to go so that you take a more random sample and further explore those questions. Stratified sampling, in both of them, you divide the population up into groups, which in this one you call strata and the other you call it cluster. But you start by dividing the population up into different subgroups. And these subgroups are ones that have the same characteristics. So it's not like, you number people off. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and all the ones are in one group or the twos are in the other group. It's more something that is already occurring with the people, like women or men. Okay, try that again. Women, there we go, or men. So you already fall in one of these two categories. Or that you have brown hair, yellow, blonde hair, whatever. You're a freshman, sophomore, junior, senior. It's something that you already fall into. Now, in stratified sample, we then pick some from each of those groups. Okay? So I took 3 women here, and I took 3 men here. Now, it doesn't always have to be the same. I could have picked 2 women and 3 men. That would have been fine too. But the point is, I take some from each. Sampling, the next one, often get mixed up because they start the same way. I divide it up into sections. Like I said, this time we call it clusters. But then I select some of the clusters and do all in there. So in stratified, if this was a stratified sample, I would pick some from all 32 of these precincts. So I might pick 20 voters in each of the precincts. But because this is a cluster sample, I'm going to pick these 3 precincts. So I'm going to pick 5, 16, and 28. And then I'm going to interview all the voters in those 3 precincts. I'm not going to do anything in any of the other ones. So that's what makes it cluster instead of stratified. Alright, so here's your last group. Again, hit pause, put what you think, and then come back and get the answers. Again, as usual, I'm going to use initials. So random will be R. Systematic, I will use S. Convenience, I will use CO. Stratified, I will use ST. And cluster, I will use just C. So the first one. Using random digital dialing, researchers called 3,258 Kingsport residents and asked what grocery store chain they prefer. I used random digital dialing, so I had a computer picking it, and I didn't have any choice over what the numbers were. So that is a random sample. Corn is planted on a 12-acre field. The field is divided into half-acre subplots. Alright, the fact that we're dividing it into half-acre subplots makes me know it's either stratified or cluster. A sample of corn is taken from each subplot, so that makes it stratified. Okay, and these last ones. Questioning people as they left the local warehouse store, a researcher asked 523 people about their exercise habits. This is a convenient sampling. It's just catching them as they're leaving. Not sure why they picked a warehouse store. Seems like a local gym or something would have been better, but whatever. A newer subdivision is divided into 12 subsections based on location. 4 of the sections are selected to determine opinions about the new HOA, Homeowners Association fees. Alright, the subdivision is divided into 12 subsections, so that tells you stratified or clustered. 4 of the sections are selected and asked, so this is a cluster. This one's convenience. I can't remember which one I said was the C. A line manager at the local manufacturing plant checks every 115th ball bearing for the correct weight. Well, every 115th is like that kth thing. So this one is systematic. I'll just circle it there. Okay. Bring these notes with you to class tomorrow. Ask any questions that you have, and then we'll do activities to help you further learn this.